Bullet trains in Japan are built using maglev technology from magnetic levitation, so these are basically the levitating trains that don't have any single contact with the actual rail, but rather use magnets to levitate above the rail. In 2015, such train technology set the world record for train speed at 605 km per hour or 375 miles per hour. This is just slightly slower than a plane. Interestingly, maglev technology isn't only used in Japan. China is developing a system of maglev lines near Shanghai, but things are moving pretty slowly there. You'll be surprised, but the maglev technology has been under research and engineering for about 120 years now, and there are still only 6 commercial maglev lines in the world. 3 in China, 2 in South Korea and 1 in Japan. Anyway, a lot of tech bloggers keep hyping it and calling it the technology for future travel. And we can come to this later, but we should understand the limitations that the maglev technology has and that we have to overcome somehow. And the first problem is that we just can't use the existing infrastructure for maglev trains. We have to build a completely new system of railway lines to use this technology, and looking at how fast some countries develop their train systems, I believe we'll need another 1,000 years for that. Also, operating maglev trains is very expensive, and I don't think there is a single company in Asia that actually earns money from operating a magnetic levitation technology for commercial use. The energy that is used for magnets to keep the train up in the air is not that huge. The most energy is used to overcome drag issues. When a train that weighs a lot of tons flies at the ground altitude with the speed of 500 km per hour, it develops impossible drag, and the engines have to work hard to overcome that drag. It isn't the issue for classic railway trains that hardly ever go faster than 200 km per hour. In those cases, engines work to maintain the speed of the huge machine and not so much power is wasted. Maglev technologies are usually useless at low speed of up to 150 km per hour. This makes the system use a lot of power to just keep the train levitating, but at higher speeds of about 250-300 km per hour, the power for levitating the train is minimal. This is considered the perfect speed for such trains, as the drag is also optimal. At higher speeds, the air drag makes it impossible to avoid power waste, but there is one technology called VecTrain that will try and eliminate that factor. VecTrain is basically Hyperloop, so this is a system of vacuum tubes that have no air, so there is no drag in these tubes. If the train travels through such tubes, it's very likely that the energy consumption will be minimal, but the cost of construction is ridiculously high as of now with the use of current technologies, so we don't see Hyperloop tubes being constructed in every other country. Without the VecTrain technology, there is a very low chance that we'll see new maglev lines anywhere else in the world. But if we manage to find a cheaper way to construct such tubes, there are numerous advantages of the maglev technology. First of all, maglev is cheaper to operate and maintain. It doesn't burn fossil fuels, and it can be a zero-emission technology with relatively limited use of power. Also, the rail will not require a lot of maintenance as well as the train systems, because there is no physical contact between the train and the rails when the machine is moving. Additionally, maglev trains can potentially develop much higher speeds than traditional high-speed trains, and in theory, these maglev lines could be constructed anywhere in the world. There are no climate or weather limitations, especially if we're talking about vacuum tubes. Also, if you ever traveled on a high-speed train, you know that they are quite noisy. The noise is not about the wheels touching rails, but about the air drag. So if we are talking about VecTrain maglevs, the noise should be minimal, not only for passengers but also for the environment. This is extremely important in some areas. One more benefit is that vacuum tubes with maglev trains will be very safe. First of all, they are computer controlled and the operators will just observe the dashboards and confirm that everything is in order. Secondly, they are separated from any other traffic, The maglev lines are usually elevated and they never cross with other traffic because the magnets must be in constant contact with the train to keep it in the air. So these trains will require a totally separate ecosystem that will not interfere with any other transport or people. So the risks are minimal. The price of building 1 kilometer of the non-Vectrain maglev line ranges from $20 to $100 million depending on the terrain, technology and also corruption risks. Reportedly, Hyperloop should cost about $60 to $80 million per 1 mile. Anyway, this means that countries have to invest billions of dollars to bring those maglev trains to life. While Japan is keen on new technologies and wants to be among the first ones to implement them, other countries are far more sensible in terms of investing in maglev lines, at least for now.